Let's prove type preservation. So if expression E has a type C and it reduces to another expression E prime, then this type preservation guarantees that expression E prime preserves the type C. So that's the type preservation theorem. And we'd like to prove this statement by rule induction. And we have this familiar form: if J and J prime hold, then another judgment J double prime holds. So we have to rephrase it into either if J, then J prime implies J double prime, or we could apply rule induction to this judgment J prime, in which case you have if J prime, then J implies J double prime. So first, we have to decide to which judgment of this one and this one we should apply rule induction. For this particular case, it turns out that either option is fine. You can apply rule induction to this judgment, or you can apply rule induction to this judgment. And whichever path you take, you can complete the proof. So for this lecture, let's apply the rule induction to the reduction judgment. But remember that it's also okay to apply the rule induction to this judgment, although we are going to apply rule induction to this judgment. So the first step is rephrase the statement into more amenable form, which is, in our case, if expression E reduces to E prime, then this assumption implies this typing judgment, E prime C. Then how do we prove? Proof by rule induction on this reduction judgment. Now we have to go over each case. So perhaps there are many cases. And the question is, which case do we want to consider first? So we have quite a few cases, from the simplest case to the most challenging case. And it turns out that although it sounds counterintuitive, you want to consider the most challenging case first. Although your instinct perhaps says that you want to consider the easiest case, the simplest case first. And the rationale is, we are trying to prove this statement, the type preservation. We believe that this statement is true, rather than refuting it, believing that it is false. Perhaps this statement is provable, it's true. So we are trying to establish its truth. Then it makes it to consider the most challenging case first. This is the most challenging, and this is quite easy. And the question is, do you want to consider this easy case first, or do you want to consider this most challenging case first? And the answer is, you want to consider this most challenging case first, because you are trying to prove the truth of this type preservation theorem. And why is it that? Because eventually you will have to consider all these cases anyway in order to complete the proof. So therefore, there's no reason not to consider the most challenging case first. Eventually, you will have to consider this case anyway. If there is something wrong with this type preservation theorem, so for instance, there is a bug, then things are different. You will not be able to complete the proof. But you believe that you can complete the proof. So therefore, this case, the most challenging case, should be the first one to visit. Although I admit that it sounds quite counterintuitive, everybody wanted to consider the easiest case first. Now, what about, let's just say you have another statement, but you are now, this time, you are trying to refute it. You believe that, you believe that this statement is wrong. You believe that there's some bug in this system, and you are trying to locate the source of this bug. You are trying to refute it. In this case, you want to consider the easiest case first rather than the most challenging case, because it may be that you never need to consider the most challenging case. For example, in the course of analyzing the easiest case, you might find the bug if you are lucky. So in this case, where you want to refute the statement, you believe that there is a bug in this system and you believe, so therefore the statement is unlikely to be true. If that's what you believe, you want to consider the easiest case first. In our case, we are trying to establish the truth of this statement. Therefore, you want to consider the most challenging case first. If you manage to, if you manage to prove the most challenging case, then you can rest assured that the remaining cases are okay because they are less challenging. They are no more challenging. They are no more difficult to prove than this case. So that's the idea. So for our case, we'd like to consider the most challenging case first. And then what is the most challenging case first? What is the most challenging case? All right, so what is the most challenging case? The most challenging case is, for this reduction judgment, it is the case where beta reduction is involved. Namely, assuming the call-by value, you have this lambda application reduced it to value v for x in expression E. Then you assume this one. So let's assume gamma, what is the expression E? This is the expression E. So lambda x a dot E value v. This is a type C. So this is going to be assumption. And you somehow find, you should somehow show that this expression v for xe maintains the same type C. This is what you needed to show. Okay, and this is the most challenging case. So once you complete this, the most challenging case, then you can rest assured that all the remaining cases are going to be fine. So let's further analyze this case. So this is the assumption, and this is what you needed to show in the end. And if you think about this judgment, this is the only way to prove this judgment. That is, you apply gamma elimination rule. So you have gamma lambda abstraction with the type A arrow C, and you have value V of type A. So you can expand the derivation tree. And moreover, if you think about the first premise, this is the only way to prove the judgment. So by expanding the assumption, you have this partial derivation tree. And the goal now is, by exploiting anything you have inside this partial derivation tree, you needed to show this judgment. So the problem reduced it to the proof of this step. Okay. And it turns out that